Hey, welcome back to Fat Mama Physics. In this video, we are going to apply Kirchhoff's laws and me giving you some strategies on how you can analyze circuits. So here in front of you, I have a few diagrams of circuits. At this point, I hope you know some basic symbology, like what a battery looks like, what a resistor looks like, what happens here at a junction, or what are these junction points over here. Hopefully you also have an idea what Kirchhoff's current or voltage law is at this point. So this video will be just focused on applying them in situations. So I'm going to give you a basic tip in this video, how to start off or how to generally approach solving a circuit. Here I have a first circuit here, which there's a battery and there's a resistor connected to it. This one is the most simplest case you can ever get. And of course, all you would have to do is use Ohm's law, which is V equals to IR, current times the resistance of this resistor, to figure out whatever is missing in your formula. So in this case, we are going to assume that since this is the only resistor that is in the circuit, then the potential drop across this resistor will be exactly that of the battery, assuming everywhere along the wire there is very little to no resistance. So the potential drop across that battery being 12 volts, which we can substitute in here. Let's say we're given the resistance of the battery in ohms. Let's say it's 3 ohms. Then we're giving the resistance as well. Then we can use that to help solve for the current. Okay, so that's very simple. And ideally, all of the circuits that you solve, you want your circuit to look like that, or at least a representation of that, so that you can solve for the current that is going through your battery, or let's call that the total current. Because once you know the total current going through your battery, you can figure out how to divvy up that current based off of whether there are junctions or not, or whether you just have one complete loop, just like the next example. The next example here, we have 3 resistors connected in series. And what that means is essentially the total potential drop across all of these resistors combined from here all the way there is going to be 12 volts, which means this 12 volts will get divided amongst these 3 resistors in which we don't know how. But it seems like in this question all the resistors are the same. So true, you could just divide the total potential drop by 3 to give you the potential drop at each of these resistors. But let's assume we don't know what the resistors are, or how big the resistance is in each of them. How can we deal with this kind of case? Remember what I said before, you always ideally want to find the current going through the battery, which is the total current. So how do we make this circuit look like that circuit, or to some equivalent of that? Hopefully you've learned before how to combine resistors into finding a total equivalent resistance or resistor. So what that means is I could take these 3 resistors and combine them into one big one. I know it's not going to be the actual circuit itself, but it helps you solve some problems that, for example, finding the current through the battery. So what that means is I could redraw this entire circuit, and then I'm going to draw a big fat resistor right over here, and I'm going to call this one the R total, which is the total equivalent resistance, meaning if I just basically collapse the circuit down to essentially just that one resistor. For series, resistors in series, we know that the total equivalent resistance is all of the resistors combined. So let's call that R1, R2, and R3. That would just be R1 plus R2 plus R3. I think of it as traffic jams. If there's 3 traffic jams for you to get to wherever your work or school, then the traffic's going to get worse and worse after you go through each traffic jam. So the resistance is going to add up in this case. So luckily, if the resistance here, if it's just 3 ohms, and I know I could have just divvied up the potential difference there. But let's say we have 3 ohms, then I would just add all 3 ohms over here. No significant figures. Unfortunately, I'm running out of space. This is going to give me 9 ohms total. And knowing this 9 ohms is important because now that I know that total resistance in my circuit, this case now looks like my first one, which if I want to find the current, the total current through my battery, then essentially I just have the potential equals the I total, the T for the total here, and then R total for the total resistance. So here I have 12 volts, here I have 9 ohms, and I just solve for the current, which is just fine. I'll do it. And this is just 12 volts divided by 9 ohms. Someone can do the math. I'm a little bit slow today. Of course, aren't we always slow? 1.3 repeated for the amps, okay? So remember, it's collapsing the circuit down to that one equivalent total resistor. Now that you know the current, which is 1.3 repeated amps, that allows you to solve for other things in the circuit, because this is why I get to show why that's important. Because your current is going to leave this battery from the positive terminus, and as it goes around the circuit, this current here is going to be the same across that first resistor. It's going to be the same across this resistor, the same across this one before it goes back to the battery. It makes one complete loop. It doesn't get divided. Remember, current is just moving charges. Imagine a group of friends going through the mall. If they're going to go all together like a bunch of these charges, then they're going to hit every single resistor. The current, the group of friends, will go through exactly every single point along this wire, meaning that all the charges will remain within this loop, so therefore the current is the same throughout the circuit, the same across every resistor, which means that if you know the current across each of these resistors, then you are able to find the potential drop across every single one of them. So this is going to be I total times R2 using Ohm's law, and etc. Of course, we all know it's all going to be the same because these all have the same resistance. All these resistors have the same resistance. But if they don't, then that's how you would find the potential drop across every resistor, and potentially finding the power dissipated by that resistor as well. So that's the power of finding the total current going across the battery. All right. Now let's take a look at a parallel series of resistors connected in parallel. So again, we want this setup to look like exactly the first guy over here, which means we have one equivalent resistor connected in series with our main battery. Kind of looks like this. Okay, I'm going to save a bunch of spot on the side for writing there. But we know that finding the total equivalent resistance for resistors in parallel is going to be different. And I'm going to use a space down here. The relationship is 1 over RT is going to be 1 over R1 plus 1 over R2 and 1 over R3. So that's the relationship between the total resistance of when we combine all resistors here together. Let's try that out. We have 1 over RT. This is going to be 1, and I'm going to use that 3 ohms just again. And I know it's going to be the same. Doesn't really matter, okay? So this is going to be 1 over we know what that is. 1 over 3 plus 1 over 3 plus 1 over 3. And you got it. That's just going to be 3 over 3, which is just 1 ohm. Hey, guess what? Sorry. A lot of times I make this mistake too. That's equal to 1, but careful, 1 is equal to 1 over RT. So if I want to find RT, I have to take the inverse of 1. So I have to flip this, take this to the -1, take this side to the -1. I get RT is equal to 1 ohm, since 1 over 1 is just 1 ohm. But imagine if you got, say, a big number here, then if you take the inverse of that, then you get a smaller number, which is Interesting, because you might have noticed the equivalent resistance in our parallel series is, our parallel circuitry is less than the resistance in our resistors that are put in series. You're thinking, interesting. Because, well, if you think about it, imagine you're trying to go to work. Imagine there are multiple ways you can go to work. Well, some of these cars coming along here, they're going to get screwed over in this traffic jam. Some of them will get screwed over in this traffic jam, and some of them will get screwed over in this traffic jam. But overall, you've divvied up the cars going to work so that every traffic jam won't get worse, meaning that you're kind of divvying up the load across all of these different paths before they come back together and get themselves to work. Okay? So the total resistance decreases because you have more. Think of it as you have more choices of going to work. So overall less resistance that you would experience overall. Okay? So the total equivalent resistance here is 1 ohm, meaning that if we want to find the total current going across this battery over here with 12 volts, then we just have to do V equals to I total times R total. And since R total is just 1 ohm and V is just 12 volts, well then the I total, the total current going across this resistor, is going to be also 12 amps. That's a big current, to be honest. This is where it gets a little bit interesting, because now that we know the total current going through this battery, let's try to go back to this original circuit to analyze this a bit. So with this 12 amps, did I say ohms? 12 amps of current, it's gonna, imagine a group of friends again, or a group of cars, or whatever, or charges for that matter. As they come to this junction, we're going to lose some of them to this junction. Some of them are going to go here, some of them are going to go there. So all these 12 amps are actually going to get separated, meaning that the current through here is not going to be 12 amps. It's going to be less than 12 amps. Same as the current going through here is going to be less than 12 amps. Of course, if we add the two currents that are being split up over here, they should give us 12 amps total. This current going down here is going to get split off there and split off there. So whatever's remaining is going to get split off again. And this current going, so then you'll get a bit of this current, you'll get a bit of these 12 amps going through each of these resistors, which we don't know how much is which. But once they go through these resistors, when they come back, they will connect here. Look at this junction connecting here. So these two currents are going to add up together again. And then these two currents are going to add up here again. And guess what? It should give us the total 12 amps, then returning to the battery once more. So the difficult part in this one is finding the current across every resistor, versus in the previous case with it in series, the difficulty was finding the potential drop. Because you're like, well, how do we find the potential drop in this case with parallel resistors? We know that since these resistors are connected in parallel, the drop here is all going to be the same. The drop here is going to be 12 volts. The drop here is going to be 12 volts. And the drop here is also going to be 12 volts. Meaning that if you know the resistance in each of these resistors, then you can find the current across each of these resistors by using Ohm's law, V equals to IR. Since we know what the resistance is, 3 ohms, then we can use this one. This is 12, and then R is 3. So 12 divided by R is just going to give us 4. Our current here is going to be equal to 4 amps. And since the resistor here is the same, this is also going to be 4 amps. This is also going to be 4 amps. And hey, if you add 4 amps plus 4 amps plus 4 amps, once they come back to the battery, it's a total of 12 amps. Which makes sense. It's a good way to check your answer at the end. So just to reinforce all of that, here's a quick little there's a quick part of this video I'd like to show us. So take a look at a series of resistors, just like these 3 light bulbs. Notice that imagine the when I talk about voltage drop, voltage gain from the battery, every voltage drop, as you add all of each voltage drops from each of these resistors or light bulbs, that gives you the total drop across the battery, or gain, okay? So, but in each of these cases, notice it's the same current that's going around the circuit. Ignore that, that's broken there. But essentially, yeah, if you take a look at every time all of these little charges going across the circuit, they have to go through each light bulb, essentially. Versus if you compare that with a parallel case, the voltage drop across each light bulb is going to be the same, because imagine you raising one side of that circuit up, and that drop coming down, and then the currents collecting here, coming back to the battery. So that's where you get the split in the current, but the same drop for potential difference before it comes back to the battery. Okay, so I really like this visual. Thumbs up to Eugene. I can't pronounce that last name. So this person does a lot of great visualization videos for physics. So here we go. Okay, so hopefully, again, just to quickly summarize. Great way to tackle a circuits problem is to try to combine, if anytime when you're trying to solve a complicated circuit, always try to make the circuit more simple. The simpler the circuit, the easier it is to analyze. And once you have a simple circuit, you might have found out a few things. Then you can extrapolate back to your original circuit and maybe use some of your new information you found to figure out other pieces of the puzzle. Okay? Well then, hopefully you enjoyed this video. I enjoy circuits and analyzing them with you. I wish you the best of luck. And Fat Mama Physics signing out.